So this video is to go over investigation 7A. So in this investigation you learn how to model reflections using paper folding techniques, model composition of reflections and classify the resulting transformation as a reflection, rotation, translation, or a combination of transformations, understand properties of reflection, translation, rotation in the plane, identify fixed points for a given transformation or composition of transformations, and also use isometry to prove some triangle congruence criteria. So vocab and notation, it didn't really come out very well, but we have a lot of vocabs in this investigation, so check that out. So the big idea of this investigation is the new definition of congruence with isometry, and also we proved triangle congruence postulate with isometry, so now we call it triangle congruence theorem. So the new definition of congruence is two shapes are congruent if there is an isometry that maps one shape onto the other. In other words, two shapes are congruent if we can move one shape so that it fits perfectly on top of each other. In chapter 2 we have learned that if the congruence is if we can cut out some triangle or whatever the figures, and if we can put that shape on top of the other one, the other shape, perfectly, and it fits perfectly, then we call it congruence. So the new definition of congruence is kind of like the kind of more formal version of what we have learned in chapter 2. Before we get there, we need some terminology: pre-image and image. So pre-image is the original shape, which, for example, this one. So this is the original shape, which we call it pre-image, and then the copied one or translated one, we call it image. Reflection is kind of like a folding line. So if you look at this line of symmetry as a folding line, and if this is a paper, and if I fold this pre-image, then this will be on top of this one, or this will be the image of this one. And we can tell that segment AA prime, segment BB prime, segment CC prime is perpendicular to this line of reflection. And also we know that segment AR is congruent to RA prime. In other words, the length AR is congruent to is equal to RA prime, which is true for BQ and QB prime and CS and SC prime. Rotation is if you can look at this pre-image as rotating this way, okay, and we can see this is the center of rotation, and this is the angle for rotation. Those are the two terminology for the rotation. Translation. So any translation is a composition of two reflections over a pair of parallel lines. So if you can see that this pre-image is reflected over this line of symmetry, you get this image. And then if you draw another line which is parallel to the first line, and if you reflect the first image over the second line, you get this one. And if you compare the pre-image and the second image, it's just simply translated, right? A to A double prime, B to B double prime, and C to C double prime. I want you to realize that when you reflect pre-image to the first image, this C has moved, and we call that as fixed point. That's another keyword. Theorem 7.1 for part 1 says rotation is composition of two reflections over intersecting lines. So unlike the previous slide, we learned that if you reflect pre-image twice over parallel line, it's the same as translation. But what if it's non-parallel line, which is reflecting over the intersecting lines? So this is the pre-image reflecting over the first line, you get this one. And if you reflect it over the second line of symmetry, which is crossing the first line, okay, and then if you get this second image. And if you compare the second image to the pre-image or pre-image to the second image, then you'll see that it's just simply rotating. This guy is rotating this way. The second part of the theorem 7.1 says that the center of rotation, so the angle from here to here, is twice as big as the angle that is made out of two lines of symmetry. So let's say if this is 35 degrees, okay, right there, so SOR is 35 degrees, then angle A or A double prime is 70 degrees. And we proved that in the class. And some other conjectures we made in the class was there are at least one rotation in any image, any figures. So for example, if you have scalene triangle, we can at least rotate it 360 degrees to put it back in the same position. The number of rotations and reflections of regular polygon is equal to the number of size of polygons. So for example, if you think of regular pentagon, which is not very good, but if you look at this, and if you think about how many rotations you have and how many reflections we have, then we know that we can click this image into, if you click it one time like this, so this one goes to here, and 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 this one goes to here. So that's the one click. We have one rotation. And the second rotation will be if you move this one to here, so it's kind of like 2 clicks. That's another rotation. Or if you do 3, we can do 3 clicks, or 4 clicks, or 5 clicks. So we have 5 rotations, and also we have 5 lines of symmetry, a line of reflection. So this is 1, this is 2, 3, 4, and 5. Okay, so the number of rotations and reflections of regular polygon is equal to the number of sides of the polygon. So if you have 7 gons, then 7 regular gon, then we'll have 7 rotations and 7 reflections. If you have 21 regular gon, then we should have 21 rotations and 21 reflections. So the proving congruence by isometry for SAS. So how do we know that this C will be, if you fold this triangle over this line, how do we know this C will be end up on F? So let's use our old friend, which is perpendicular bisector. Now we know that this triangle is isosceles triangle. That means this line will be crossing at this one perpendicularly, so that forms 90 degrees. So if this is 90 degrees, then we know that by perpendicular bisector theorem, we know that the distance from here to here is congruent to from here to here, so we can say this is congruent to this one. So that means that C will be right on top of F. Therefore, and also we can also tell that this AC, if you move this AC to make it fit to DF, it's gonna fit perfectly, because if I move this one, move this AC around, by isometry we don't change size or we don't change shape. So that is our we are assuming that when we say there is an isometry when we move things around without changing the shape or size. And let's look at how about ASA. So I draw this one by mistake. That shouldn't be there. However, okay, well, I can't really say it, but let's not worry about it, right? So how do we know that this F will be right on top of C? Okay, if DF is a little longer than AC, then F will be ended up being somewhere over here, which will be a little, if AF is a little longer, then F will be somewhere over here. But if DF is a little shorter, then it will be somewhere over there. And that's what we know, at least, because these two angles are congruent. So F will be ended up being somewhere on this line. Likewise, we don't really know EF is congruent to BC, so possibly EF can be a little longer than BC. If that's the case, then F would be ended up being somewhere over there, but EF could be a little shorter than BC, and so BC will be somewhere on there. So we don't know where F is. However, we know that this F will be somewhere on this line and on this line. So if F is somewhere on this line, I mean on this line, extension of AC, then that means it's not going to be on BC, or vice versa. So F has to be right on top of C, and that's going to prove the congruence by isometry for ASA. How about the last one? We know that SAS, right? So DF is congruent to AC, and CB is congruent to FE, and DE is congruent to AB. So we know that, but we don't really know that if this angle matches, or these angle matches. But if these two angle doesn't match, then it will be possible that if we have C over here, but F will be somewhere over here. Okay, but we know that if you draw a line like that, we know that this will be F and D and C. We already know DF is congruent to AC, so this will be congruent to that one. And if you pay attention to this one, this has to be isosceles triangle. Okay, if this is isosceles triangle, that's for sure. If that's the case, then this line has to be crossing this line at 90 degrees. Okay, so if this is 90 degrees, then by perpendicular bisector theorem, then F2, this intersection point, is congruent to this intersection point to C. Therefore, this is contradiction. So these F and C must be on the same points. So that proves the congruence by isometry for SSS. So isometry means that it's the rigid motion and moving a figure without changing its shape and size by translation, which is sliding, reflection, which is flipping, and rotation, which is rotating, rotating, or composition or combination of any of these three. Okay, so it's possible that you can have 2 reflections, or 5 reflections, or 5 rotations, or 2 rotations and 1 translation. So when you reflect an object over a line, what properties of the object are present in its image? Well, we know that the length and angle measures are preserved. In other words, size and the shapes will be unchanged. Now the question is, what happens when you compose 2 reflections, 3 reflections, or 4 reflections? So if you have a triangle like that, if you have a triangle like that, and if you reflect it over one here to here and here to here, that's going to be the same as translation. But if you do one more time, what's going to happen, right? So it's just simply translating and then reflecting, or reflecting and translating. What if you do that with reflect 3 times over intersecting lines like that? So if you reflect it over intersecting lines twice, then we have learned that it's just going to be a simple rotation. But if you reflect it one more time, that means you can rotate it and then reflecting once, or reflecting it and then rotating, or that's that. So the composition of 2 reflections is a translation or rotation, and the composition of 3 reflections is either a reflection or a transformation that reflects figures across a line and translate them parallel to the line of reflection, or composition of 4 reflection is a translation or rotation. So yeah, that's it.